Welcome, and settle into a quiet place within yourself, where the lights feel dim, the air is still, and the only movement is the slow turning of your attention toward a soft, unhurried story. Imagine yourself watching a tiny green indicator on a silent test bench. A single battery cell resting like a calm sea under glass. And the long, unremarkable patience of chemistry carrying on at the gentlest possible pace. If you enjoy these calm journeys through sleepy science, you can like and subscribe to keep this soothing library growing. And you're warmly invited to use the playlist linked in the description to keep learning as you drift. What city country are you watching from right now? You're here with a battery that is not dramatic. It is not the roaring surge of a storm nor the blaze of a fire. It is a quiet bowl holding a measured amount of energy, like rainwater gathered after a light drizzle. In the hush of the lab, it sits and waits. And in waiting, it changes. Every small change has a cause. And every cause has a texture. And the texture is the slow work of electrons and ions moving along pathways that we can't see with the eyes, but can sense through careful instruments that whisper their readings into a log that fills line by line by line. Imagine a bench the color of soft slate, with pebbles resting in smooth arcs, and a faint scent of clean metal and a hint of plastic, not sharp, but familiar. Somewhere, a temperature chamber hums like a distant refrigerator, steady and even, keeping the air at a precise level of warmth, because warmth guides chemistry as gently as sunlight guides a plant through the day. The battery cell is modest, perhaps sealed in a rectangular pouch, perhaps wrapped in a small cylinder, the kind you might hold without thinking, even as its interior holds a whole landscape. Inside, there are sheets of carbon teased into order, thin layers of metal oxides aligned like pages of a quiet book, a polymer separator as soft as a veil, and a clear liquid solution that bathes everything, a solvent carrying a salt that dissolves until an invisible crowd of charged species is ready to move. Long before this quiet moment, during its first formation cycles, the battery learned to protect itself. The first time it was charged, the electrolyte solvent touched the carbon of the negative electrode and changed, splitting and recombining, leaving thin fragments behind, making a coat, a boundary, a layer that we call the solid-electrolyte interface. It is not a solid like rock, nor a liquid like water, but something in between, a fragile varnish, good at letting tiny lithium ions slip through, but not so generous with electrons. This coat is a gate and a guardian over time it grows. Not fast, never fast. It grows as if counting the beats of a whisper. It thickens as a sheen of material the color of concepts rather than paint, made of salts and carbonates and small polymer strands, adapting itself to the surface below like dew on a leaf. Capacity is the amount of charge the battery can store, and we think of it as a number, neat and round. At the beginning, the number is generous, measured in milliampere hours, the way a careful baker measures flour. With use, and with time, even without use, the number nudges downward, never in a hurry, more like a slow settling of a cushion than the drop of a stone. Some of that change comes because the guardian layer uses up a few lithium ions every time it heals a scratch, or fills a tiny gap. Some comes because parts of the internal structure lose touch with each other. A particle cracks, and the crack is a path for the liquid to carry away more material, or a piece of active material becomes lonely, no longer connected to the rest of the circuit. Some comes from spreading resistance, the way a gentle pile of leaves makes it harder for a breeze to pass through. This battery ages by adding 100 tiny inconveniences that accumulate into a perceptible difference. You settle a little deeper. You watch the electronic cycler as it nudges a small current into the cell and then releases it, then holds the voltage at a plateau as if cradling a sleeping thought. The cell responds with a delicate curve. The charge rises slowly. The discharge falls like a sigh. With every cycle, the curve looks familiar, only the faintest shift with time. If you overlapped all the curves, you would begin to see a tiny drift, like the shoreline moving millimeter by millimeter over years of gentle tides. That drift is the signature of 100 mechanisms, each one tedious in its own way, each one a humble servant of thermodynamics. In the graphite anode, lithium ions tuck themselves between layers. They're like polite guests slipping between pages of a book. They enter and exit through narrow spaces, guided by concentration gradients that are subtle enough to make you think of perfume dissipating down a long hallway. When the battery is charged slowly, each ion has time to find its place and rest. When it is pushed faster, or the air is colder, or the state of charge is already high, some ions have trouble fitting and may pause on the surface. If the pause lasts long enough at the wrong conditions, those ions can settle as a thin metal deposit, a frost that was not intended, which takes lithium out of circulation and raises risks that engineers work very carefully to avoid. But here, in this careful scenario, the charging is gentle, the temperature stable, and the chance of that frost is kept very small. The chemistry leans toward what is predictable and calm. On the cathode side, in many modern cells, there is a layered metal oxide, or a polyanion structure, something like lithium nickel manganese cobalt oxide, or lithium iron phosphate, or another well-behaved framework. Each holds lithium in predefined rooms, and each room has a view at a different voltage, depending on its chemistry. As the cell charges and discharges, lithium slips in and out of these rooms, and the frameworks breathe a little, expanding and contracting by tiny amounts. As the guest count changes, over time the repeating breath can create small strains. Particles chip at their corners or develop hairline cracks that are too small to see but large enough for the liquid to find. The liquid is a deliberate blend, often a mix of carbonates with a salt like lithium hexafluorophosphate that loves to dissociate into helpful ions. The salt also carries a quiet compromise. It tolerates water poorly. When traces of moisture sneak in, reactions begin that produce acidic species, and those species nibble at the elegant surfaces, particularly at higher voltage, dissolving tiny amounts of transition metal that later wander and deposit somewhere else, often near the anode core, where they interfere with the smooth motion of lithium. Calendar aging is the name we give to time's effect when the battery is simply stored. No cycling, only waiting. It is the slow thickening of the protective layers, the quiet drift of components into slightly different arrangements, driven by the fact that nothing stands perfectly still at the atomic scale. This is the battery aging in real time, even at rest, an edgeless activity that is in no hurry, a story of molecules finding marginally lower energy states in increments too small to feel. Cycle aging is the name we give to the wear that comes from use. Turning on a lamp with a battery is like walking down a familiar path. Doing it once is nothing. Doing it 1,000 times very gently is still mostly nothing. Doing it quickly on steep hills in the heat or cold begins to leave marks. Both kinds of aging meet in the ledger of capacity and resistance. Temperature writes its commentary in a predictable hand. Warmer conditions speed many reactions, not because they are reactive in a fiery way, but because molecules vibrate a little more, and the increased motion helps them cross the small barriers between one state and another. If you picture a line of beads separating two bowls, heat is the small nudge that makes a bead more likely to skip the line and fall into the other bowl. In storage, this means the protective layer grows thicker faster at warm temperatures. In use, it means the electrolyte and the electrode surfaces talk to each other more often, crafting new compounds and consuming the old ones. At lower temperatures, motion slows and reactions hesitate, but lithium ions also move more slowly through their hosts, which can lead to congestion during charging and discharging. A thoughtful balance lives in the middle, a comfort zone where the battery is with a kind of serene steadiness. Voltage is another quiet influence. Holding a battery at a high state of charge is a bit like keeping a violin string pulled very tight. The instrument may be ready to sing, but the tension invites subtle changes to the wood and the string over time. In the battery, high voltage can encourage the electrolyte to nibble at the cathode surface, forming its own protective film, sometimes called a cathode electrolyte interphase, which is, like its anode cousin, a mixed blessing. It slows the more damaging reactions, while, in growing, it consumes reagents and increases resistance. A lower state of charge means less of that high voltage tension, less chemical eagerness, and often a slower drift in capacity. This is why many devices age more gracefully when stored partially charged, somewhere around the middle of their range, patiently waiting. If you imagine an afternoon in the lab, the figure on the monitor is a plot, a neat graph with a soft line that is more slope than cliff. The y-axis is capacity, and the x-axis is time, perhaps in days or cycles. Each point was taken slowly, like taking a pulse at rest. The dots join to tell a story you can summarize in a sentence, but inside the sentence are seasons and afternoons and 100 small variations. The protective film grows by the square root of t, not because it wants to be mathematical, but because the rate at which simple molecules arrive at surfaces depends on a gradient that flattens as the layer thickens. The first hours show the biggest change, then the steps shrink like footprints fading on a shore where the water is barely lapping at your ankles. The engineers who build battery models use this behavior to forecast the future, not with drama, but with a comforting arithmetic that helps them design devices that age with dignity. The test bench gives off a faint warmth. The cables are still. A tiny blue light blinks with a long, slow cadence. Nearby, a notebook lies open with a pen resting at an angle, as if it just finished a sentence and decided to take a nap. You walk quietly past a shelf of cylindrical cells, each resting in a channel like beads in a gentle abacus. No one cell is remarkable. Together, they create a chorus that is only audible through numbers. The numbers would be boring if you wanted excitement. They are lovely if you crave quiet. Electrochemical impedance spectroscopy has a name that feels like a long exhale. In practice, it is a soft test. The instrument whispers a tiny alternating signal into the cell and listens to how the cell responds at different rates, different frequencies, like tapping a sleeping violin with a fingertip at various places along its string. The spectrum that returns is an arrangement of arcs and lines, each tied to a process inside the cell. The rapid dance of ions in the liquid, the slower entrance and exit from the protective layers, the even slower movement within the solid particles, and the slowest of all, the drifts related to diffusion over longer distances. As the battery ages, one of the arcs swells. The shape shifts by small degrees. The low-frequency line tilts A, then a little more. Power fades, not because the energy is gone, but because the path has grown tighter, the corridor narrower. It is like walking through a hallway lined with soft curtains. As more curtains are hung, the walkway is the same length, but it takes a little longer to pass through. The ingredients of the electrolyte each bring their own temperament. Ethylene carbonate is thick and kind, forming sturdy layers on graphite, but it is viscous, which slows ion movement unless blended with thinner partners like dimethyl carbonate or ethyl methyl carbonate. Additives used in small percentages act as diplomats, sacrificing themselves early to form protective layers with desirable properties, smoothing out rough edges, making the boundary more resilient. Vinylene carbonate might be one such diplomat, fluoroethylene carbonate another. They are like the first paint on a new wood surface, the undercoat that gives the top layer something to hold on to. Without them, the film might be patchy and the battery would age in a messier pattern. With them, it ages with a certain ceremonious monotony. Every part has a role. The binder holds the particles together on the copper or aluminum foil that serve as collectors. It is a polymer with a gentle grip, allowing electrons to move from particle to foil, while accommodating tiny shifts in volume. The conductive carbon forms a network within the electrode, connecting islands into a continent. Over time, repeated cycling and slight swelling can loosen connections at the tiniest scales. An island that once had two bridges may end up with one and then none. When that happens, those particles still contain active material, but they are cut off from the conversation, no longer able to send or receive electrons. This is loss of active material by isolation. It is not dramatic. You would not see a spark. The measurement shows it as a hair's breadth reduction in capacity, one among many. If you close your eyes, you can picture a tiny lithiation front moving through the particles of graphite like a twilight line moving across a field. It is not a wave, it is a progression of occupancy. Lithium finds a spot and waits, As it waits, other ions come and fill adjacent spots. On discharge, they leave in reverse order, not perfectly, but well enough that the pattern is repeatable, like a gentle breathing exercise. The shape of the voltage profile, with its small plateaus, reflects the order in which sites fill, a quiet signature of the host material's inner architecture. Over the months, the plateaus shift slightly because the surface is no longer as fresh, and the entrance to each room is a touch narrower from the soft buildup of the protective layer. Like a well-loved book, the edges are a little worn, and the pages turn with a hint of friction. Across the aisle from the cycler, there might be a safety cabinet where cells are stored at different states of charge and temperatures. Each drawer is labeled. Each cell wears a sticker with a simple code. Every morning, someone notes the open circuit voltage, a single number that is a quiet summary of the cell's internal state that day. Over weeks, you can see the trend. The number drains very slowly if the temperature is cool and the voltage moderate. If the temperature is warm and the voltage high, the drip is faster, a steady trickle that is nonetheless quite slow as human senses go. The story is the same. Kinetics gently accelerating with warmth. The chemical eagerness rising just enough to change the outcome over months and years. You picture a phone that was new and now is older. The first day, the charge lasted until late evening. Months later, it reaches afternoon before it asks to be charged. There is no drama. There is only arithmetic. The battery's coulombic efficiency, how well it gives back what it receives, has always been slightly less than perfect. Imagine the figure hovering at 99.95% per cycle, an excellent number. Every cycle, only a tiny fraction is lost to side reactions. That number multiplied by hundreds and thousands of cycles becomes meaningful. The rounding error becomes the point. Ambitions for longer life live in the territory of that last decimal place, which is why engineers obsess over the details of the protective layer, the purity of the electrolyte, the exact shape of the charge and discharge current, and the temperature, because all of these influence the quiet fate of that remaining fraction of a percent. There is a phenomenon called lithium plating that we pass by gently. It occurs when the anode cannot accept lithium ions quickly enough, often at low temperature, high charge rates, or when the anode is already near its capacity. Instead of intercalating into the graphite, metallic lithium deposits on the surface. In the calm scenario we inhabit here, the charge is slow, the temperature comfortable, and the anode is never driven to that edge. The battery management system in a modern device listens and responds. It limits current when the battery is cold. It keeps voltage within safe bounds. It may even slow charging as the state of charge rises, the way you cradle a glass more carefully as it becomes full. The well-known constant current, constant voltage protocol is a gentle rule. First fill at a steady rate, then hold at a set height, letting the level reach the brim slowly, while the current tapers naturally. This softness helps the protective layers grow in an orderly way, reducing the chance of rough protrusions or chemical imbalances. In some cells, silicon is added to the graphite to increase capacity. Silicon welcomes more lithium per gram, but it swells when it fills, expanding and contracting with a bigger amplitude than graphite can manage comfortably. The binder has to hold the silicon particles as they breathe, and the protective layer must adapt to a changing surface. The result, if not handled with careful design and gentle use, is a protective layer that cracks and heals again with each cycle, consuming more lithium and solvent to rebuild. With well-chosen particle sizes, binders and electrolytes, and with tamed charge profiles, the swelling can be accommodated, and the benefit of higher capacity can be enjoyed in a balanced way. The chemistry still ages in real time. The story remains one of patience. Some chemistries are more stoic. Lithium iron phosphate is like a solid old friend who prefers predictability to novelty. It holds lithium in a lattice of iron, phosphorus, and oxygen, sharing electrons in a way that keeps the structure robust. The voltage is steady, and the cycle life can be long. Layered oxides like NMC and NCA carry higher energy, but they become a little more reactive at higher voltages. And so they ask for a level of care that suits their higher ambitions. Each chemistry ages in its own accent, but all are shaped by the same sleepy processes that paint surfaces with passivation and gather scattered molecules into low-energy arrangements. You might imagine looking through a high-powered microscope that is actually a layer of mathematics and inference. No eyes see the SEI directly in the moment. They see its effect. They see how the charge transfer resistance curves upward, how the initial drop in voltage during discharge is a little larger, how capacity at a given current is a touch smaller. They also see gas formation at times, tiny bubbles in pouch cells that cause a gentle swelling of the foil. That gas is often the result of electrolyte decomposition, pieces coming apart and recombining into light molecules that prefer to float rather than dissolve. In careful designs, especially with additives that guide the chemistry, this gas is minimal and the swelling is faint, a symptom that can be measured, logged, and interpreted as another marker in the aging map. The copper of the anode current collector is sturdy at ordinary potentials, but if the battery is discharged past its intended lower bound to very low voltages, copper can dissolve and plate elsewhere, an unwanted journey that can weaken the structure. The aluminum of the cathode collector is generally stable across the allowed range, another quiet choice of materials that makes long life more likely. The separator, a delicate membrane of polyolefin layers, keeps the electrodes apart. It lets ions through like a filter letting water pass while blocking sand. Its pores are tiny and their geometry matters. Too small and the resistance is high. Too large and safety is compromised. Over time, the separator can shrink slightly at high temperatures, which is why everything in the battery is carefully matched to avoid such conditions, and why the battery management system is trained to keep the battery within a safe envelope. The design is a layered philosophy that privileges tenderness over speed and reliability over spectacle. Imaging techniques have shown the gentle cracking of cathode particles in high nickel materials when driven to high states of charge regularly. The cracks are hair-thin roads that bring the electrolyte into places it did not originally reside, increasing the surface area that needs to be protected, consuming more electrolyte, encouraging more protective layer growth, and in time, leading to a cycle of new interfaces appearing as old ones degrade. The process is not malicious. It is simply the result of repeated stretching and contracting at the atomic level. The solution is to limit the extremes, charge a little less than absolute, discharge before the voltage sinks too low, and keep the temperature where molecules feel neither sluggish nor restless. Imagine a spreadsheet that holds the life of a cell in columns that go rightward further than your eye can comfortably scan. Date, temperature, state of charge, current rate, capacity, internal resistance, Coulombic efficiency, notes. Every morning a person makes tea, sits down and fills in the new row. Sometimes the numbers do not change in a way that is obvious. The difference lives under the decimal, a whisper against the white noise of measurement uncertainty. Over weeks, a trend emerges, a slope so slight that you only feel it when you fit a line through the points. This is how real-time battery aging reveals itself. It is not a headline, it is a diary. Manufacturing influences set the starting point. Particles are pressed into electrodes through calendaring, squeezed to a density that balances conductivity and porosity. The slurry composition, the binder ratio, the distribution of carbon black, the dryness of the final film, the uniformity across the web, all these lay the foundation for how the protective layer will form and how the particles will survive their cycles. The first charge is a gentle ceremony called formation, where the cell is brought to its designed voltage slowly at a comfortable temperature to encourage an orderly SEI. Sometimes formation is repeated in steps with rests in between to let the film solidify, to let the cell relax. Those rest periods are like pauses between brush strokes, time in which the solvents and salts settle into the places that suit them best. You lean back and the scene widens. Somewhere, a warehouse stores many cells. Some are at rest, some are being shipped, some are in devices on shelves. The air varies by a few degrees over the day, and those few degrees mean a little more motion in the molecules, a few more side reactions than on cooler mornings. The difference is small, but no longer negligible when measured against months and years. Some devices are plugged in most of the time, held near full charge. They age quietly under high voltage stress. Others are cycled daily between moderate levels, spending most of their life in the middle. They age quietly too, but more slowly, their protective layers finding a steadier set point. The rule behind these outcomes is simple in character, but subtle in execution. Moderate conditions lead to moderate aging. If you walk through the lab at night, you might find a shelf of coin cells made for material tests, each one a tiny circle with a crimped edge, a little silver moon. They are built to test a specific graphite or a specific cathode material, or to try an additive in the electrolyte. Each one, when measured over tens of cycles, tells a small version of the bigger story. Does the Coulombic efficiency rise above 99.9% quickly, or does it take many cycles to stabilize? Does the impediment to charge transfer grow modestly, or is the increase sharper? Do the voltage profiles remain flat, or do they show hints of polarization that increase, like a thickening in a voice? In the morning, those results inform the next trial. The routine is gentle. Meals are planned. People come and go. The batteries do their slow work, indifferent to the clock. bound instead to a rhythm set by charge and discharge, by diffusion and reduction, by the chemistry of everyday storage. In the language of equations, which we will keep as soft as possible, the growth of the protective film often follows a square root of time behavior. This means that each day contributes a bit less than the day before to the total thickness, because as the layer thickens, it gets harder for molecules to cross to the electrode, and the gradient that drives the motion becomes weaker. It is like watching a cup of tea cool on a counter. The first minutes bring more change as the temperature difference with the air is larger. The last minutes are more static, the tea hardly cooling. This forms part of why long-term storage near room temperature sees most of its change early, with the later months and years more gentle, especially if the voltage is kept mid-range. Transition metal dissolution from the cathode, which we will keep at an arm's length, quietly affects the anode. Manganese ions, for example, can move with the electrolyte and deposit within the protective layer on the anode, altering its composition and making it slightly less conductive to lithium ions. The difference is small, but adds up. Engineers design coatings for cathode particles, often with thin layers of aluminum oxide or other compounds, to shield the surface, reducing dissolution, and thus the slow cascade of effects that follows. If the cathode is lithium iron phosphate, the transition metal is iron, which dissolves less in typical electrolytes at the relevant voltages, and the aging proceeds with different emphasis, often dominated by other pathways. For devices that must live long, between 10 and 15 years perhaps, the goals are clarity and calm. Charging is managed to be moderate. The pack is kept at a comfortable temperature, neither too warm nor too cool, with liquid or air gently moving heat away. The state of charge is kept in a window that avoids constant high voltage. Cell balancing ensures all the series-connected cells age together, quietly correcting small drifts in charge. The battery management system estimates the state of health from past usage and present response, comparing measured voltages and currents to models that whisper predictions. The best compromises are invisible. The user sees a device that simply works and grows older gracefully, like a sweater that softens with wear. If you stand quietly by a window at dusk, you might think of ions as small wanderers in a landscape of repeating hills. Temperature changes the speed of their walk. State of charge changes how many ends are available. The protective layer is a gate at each village. The rules are simple and consistent. If the wanderers are rushed at the edge of town, some might gather outside rather than finding rooms in town. If the weather is too cold, they may walk more slowly and cluster at gates. If the ends are full, they wait. Patience is always rewarded with better outcomes. In the lab, patience takes the form of slow charging, long rest periods between steps and tests, and a commitment to record even the tiniest change because, in the end, the smallest changes tell the story. Not all of aging is chemical. Some is mechanical. Electrodes expand and contract with lithiation and delithiation. Even graphite, which is quite stable, breathes a little. The repeated breathing applies stress at edges and interfaces. Over time, this can delaminate small flakes, reducing contact and increasing resistance. Binders are chosen to be elastic, to stretch and recover, to prevent the loss of contact between particle and between particles and collector. In some systems, especially with silicon, binders like carboxymethylcellulose and styrene butadiene rubber help accommodate larger swings. The texture of the electrode at the microscopic scale changes over time, smoothing in some places, roughening in others. An internal landscape evolving with a slow inevitability that we improve but do not stop. Stillness returns to the bench as the cycle completes, the current tapers, and the voltage settles. There is a soft pause called a relaxation period. During this time, concentration gradients that formed under load even out. Lithium redistributes within particles and across the electrolyte, like morning mist dispersing as the sun rises. The measured voltage at rest moves a little during this period, a very gentle drift that we call relaxation. And this behavior itself contains clues to the battery's aging. Over months, the rate of relaxation changes. The curves shift their shapes. The internal resistance of the cell grows slightly, and the time constants associated with diffusion stretch. These are quiet signs on a quiet day. Some dreams of the future feature solid-state batteries with solid electrolytes that remove the liquid component that can decompose and produce gas. In a solid-state system, aging may follow new lines. Protective layers still form because anytime a reactive interface exists, there will be reactions, but the path taken by the molecules is different, and so are the outcomes. Even there, the lesson holds. Moderate conditions, careful formation, a preference for middling temperatures and voltages, and a reverence for the mechanical integrity of the system. The boredom of good engineering is a comfort, a soft blanket woven from 1,000 cautious decisions. Anyone who has used an old laptop has felt the slow change. The energy that once sustained long stretches of reading or writing now yields an early request for a charger. The charging time may not have changed much, but the runtime has. The battery has not failed in the dramatic sense. It has settled into a new capacity defined by the tally sheet of cumulative side reactions, the thickening of protective layers, the isolation of a fraction of active material, and the quiet alteration of surfaces. The same story repeats across phones, headphones, vehicles, and grid storage with different timetables and varying permissions for stress, but the same gentle laws in charge. Let your mind drift to the image of a room with many cells connected to a long bank of channels. Each channel is a pair of wires and a set of control electronics, and each follows a programmed schedule. Charge to a certain voltage, hold, rest, discharge at a certain current, rest, repeat. The cycle numbers grow slowly while a notebook fills. Occasionally, someone enters, makes a small adjustment, notes a reading, and leaves. Most of the time, nothing happens that anyone would call an event. This is exactly as it should be. Reliability is quiet. Durability is not a performance. It is the steady hum in the background of daily life. As we arrive near the center of this gentle walk, you can share a small space with the simple pace of it all, and if your eyes are heavy, that is perfect. Still awake? Comment the secret word, nebula. Now imagine measuring the same cell at two temperatures, 20 degrees and 35 degrees, storing both at 60% state of charge. After a month, the one held warmer shows a little more shift in its open circuit voltage and a little more loss in capacity. The curve that describes it is not steep, and the difference is not a surprise. The instruments are accurate, and the pattern repeats across many pairs. Now, imagine holding state of charge high, near full, even at a comfortable temperature. the pattern changes again. Drift is a touch faster. Lower the state of charge and the temperature together and the drift slows further. The invisible dram of chemistry leaks at a rate that depends on these two settings, and the simplest map is a grid where every square is a different point on the slow landscape of aging. The best squares are at moderate temperatures and moderate charges, and the worst squares lie at high charge and high temperature. Even within that, there is structure. The protective layer is a mosaic of compounds. Lithium fluoride is often a key part, a tough salt that resists many further reactions, but that also can slow lithium-ion passage if it becomes too thick. Organic polycarbonate fragments from solvent reduction create softer regions. Lithium carbonate, a familiar compound, appears too. The exact ratio depends on the additives, the salt, the water content, the type of graphite, and the current used during formation. When the mosaic is well balanced, the layer is uniform and thin. When it is not, current concentrates at protrusions, and rough spots can grow during cycling. The aim is to keep any roughness gentle and to allow the current to spread broadly across the surface like rain across a wide field, rather than a gutter under a high spout. Aging also lives in the corners of operating protocols. Fast charging is convenient. It asks the battery to accept a lot of current in a short time. The management system controls this by watching voltage, temperature, and sometimes estimating the resistance in real time. If the system senses conditions that might lead to plating, it reduces the current. Some designs use preheating to bring the cell into a range where ions are more nimble. Others charge in steps with pauses that allow relaxation, skipping the sharpest gradients in concentration. Each of these strategies trades a small amount of speed for a large gain in serenity. At home, one can do something similar by charging more slowly at night, unplugging before the battery stays at full charge for many hours, and not letting the device overheat in a hot car or on a pillow where airflow is limited. These habits are small and only needed if long life is a priority, but they align with the tendencies of chemistry toward patient equilibrium. In laboratories and companies, accelerated aging tests are run to forecast long-term behavior. Cells are stored at a fractionally higher temperature or at high voltages to compress years into months. The results are interpreted with care because acceleration changes the balance among different mechanisms. One reaction speeds up more than another. The test gives a projection, not a perfect mirror. But even here, the rules point in the familiar direction. The more energy you keep in a battery while it rests, and the warmer it is, the more it ages. Because the living chemistry inside has more reason to seek new relationships that ultimately reduce the number of lithium ions available to do useful work and that increase the resistance encountered along the way. You might find solace in acknowledging the ordinariness of this. The battery is only one example of a larger pattern. A painted fence weathers. A book's spine loosens with repeated openings. A comfortable shoe breaks in, then finally breaks down. The specifics differ, but the motion is similar. A slow slide toward lower energy states, a relaxation of tensions, a smoothing of high peaks into soft hills. In a battery, we say loss of lithium inventory, loss of active material. impedance growth. In other contexts, we say settling, wearing, softening. The words are different. The texture is the same. The soft hum of the temperature chamber changes pitch slightly as it cycles its compressor. The lab lights reflect on stainless steel surfaces. A calendar on the wall shows days crossed out in neat pen lines. In a corner, a waste container holds safety bags where old cells are retired, discharged safely, and wrapped so they cannot short. Next to it, a box of new cells waits, sealed in a lined envelope with a desiccant pouch. The old cells and the new cells are separated by time and by their exposure to use, but not by intention. Both were designed to do a job quietly and for a long time. Both will do that job if treated with a light hand. Some people speak of memory effects, a term inherited from older chemistries. In lithium-ion batteries, the memory is not in a quirk that redistributes capacity between plateaus based on usage patterns. It is in the protective layers and the gradual changes they enforce. Devices do track usage to estimate capacity, and occasionally a calibration cycle helps the estimator more than the cell. The changes in the cell are slow and real, not easily tricked, but the path for keeping them gentle is available to us. Avoid pushing to extremes, embrace moderate temperatures, and welcome nights of slower charging that give everything inside a little more time to settle evenly. If you place your hand near a pouch cell that has aged at high voltage for months, you may feel a slight puffiness, a swelling that comes from tiny amounts of gas. The pouch is designed to expand slightly rather than build dangerous pressure. The gas is a journal entry in the history of the electrolyte, like a paragraph written in the most delicate ink. The cell still works. It still delivers energy. It has simply evolved inside its envelope, its interior map a little more complicated, a little more decorated with films and traces. In cylindrical cells with rigid enclosures, there is no swelling to feel, only measured changes in performance. The rigid form marks the shift with different signs. The story remains the same. There is a subtlety in distinguishing power fade from energy fade. Energy fade is the simple loss of capacity. The battery cannot hold as much charge as before. Power fade is an increase in internal resistance that makes it more difficult to deliver high currents without a drop in voltage. A phone that once played games smoothly may now stutter when the battery is low, not because the energy is gone, but because the voltage sags under the sudden load and the device decides to slow down rather than crash. You can think of this like a narrow pipe that still connects the same two tanks, but now has a lining that makes it narrower. The flow rate at a given pressure difference is less, even if the tanks themselves are still of useful size. The result is a preference for gentler tasks and an avoidance of the most demanding spikes. The idea that almost all loss stems from tiny inefficiencies resonates like a gentle mantra. Round-trip efficiency is high, but the fraction that is not returned is not zero. The battery bestows energy generously, but keeps a whisper of it each time in the form of new bonds at the interfaces, new molecules inside the protective layer, subtle reconstructions that are thermodynamically downhill. The whole system moves toward a state that is more stable, more set, less flexible. In the world of atoms, this is a natural inclination. In the world of devices, It means that a beautiful first day must be followed by a slightly less perfect second, and then a third, each one a little further from the starting mark, but still very useful and worthy. We might also think about the role of rest. Many tests include rest periods, both during formation and between cycles. Rest allows overpotentials to decay, concentrations to even out, and reactive intermediates to find more stable configurations. Rest is part of life, even for batteries. A cell that is always in motion, always charging or discharging, is a cell that rarely gets to flatten its gradients. If the currents are small and the temperatures are moderate, constant motion is not harmful, but the presence of rest, at least sometimes, helps. In real life, a phone sleeps on a nightstand. A car rests in a garage. The battery inside uses this time to soften its gradients and settle its surface chemistry. If you listen closely, you can almost hear it sigh in comfort. At the edges of research, details accumulate. Scientists debate whether certain species dominate the protective layer under certain voltages. They study how micro cracks form and propagate, how to coat cathode particles with protective shells, how to make electrolytes less prone to form gas, how to select salts that are robust yet conductive, and how to include flame retardants that do not disturb performance. They discuss the balance of calendar aging and cycle aging in complex duty cycles. They explore data-driven models to predict aging, feeding in temperature history, charge rates, and voltage windows, to see if the fate of a battery can be forecast with the quiet confidence of a barometer predicting mild weather. Most of this work is done in slow experiments and long simulations, punctuated by small insights that add up. You and I return to the image of the single cell on the bench, the tiny green light still on, the instrument card pulling a few milliamps for the 100th time today. The log file grows, the battery ages at a rate that would be invisible if we were to watch seconds, visible if we walk with days, and certain if we walk with years. It is the most patient of journeys, and it rewards patience in return. Treat it gently, and it will return the favor. The tedious chemistry behind slow power loss is only tedious if we expect fireworks. If we seek calm, it is soothing. It is a story where every character is polite. The solvents approach the surfaces and make small adjustments. The salts dissolve and allow ions to move like shy dancers across a floor. The electrodes open, accept, and close with minor creaks that grow over time, but never all at once. Even the management systems that watch and control are mild-mannered, keeping order without fanfare. The brilliance is in the absence of surprise, in the steady baseline that allows the rest of a device's life to carry on. In an electric car, the pack is composed of many modules, and each module of many cells. The cells talk to each other only through outward measures. No cell knows what the others hold in their hearts. The pack-level management system makes sure the individual voltages do not drift too far from each other. If one cell charges faster, it is gently bled off so the others can catch up. This balancing reduces the stress on any single cell, and in so doing, it reduces the range of aging behaviors across the pack. The pack breathes as one. Over years, it will age, but if well managed, it will do so in chorus, a smooth shift, not a discordant crash. When you next hold a device that asked for a charge earlier than it once did, you can think of this whole story like a tiny novel that was written inside on surfaces too small to see, in layers too thin to weigh directly. You can picture the thousands of cycles of minute changes, the way the SEI formed and was refined, the way cathode particles adjusted to their guests. You can picture the additions and the moves and the soft ways in which resistance rose, like a path becoming slightly more winding with each season. That mental picture can be a comfort. It is not a failure. It is a course that was always foreseen, even if few of us spend time to imagine it. The laboratory light is dim now. The last person has tidied their area, and the calendar still shows its neat lines. The cyclers hum on in low voices that might lull even restless hearts. A last note is added to the log. The cell on the bench has completed another cycle. The numbers are a little different, not enough to matter today, but enough to matter if you add them up with patience. The entire room is a poem to slow change. If you carry one practical thought from this gentle landscape, let it be light, charging slowly when time allows, avoiding leaving devices at full charge in high heat, letting them rest a little after fast use, storing them around the middle of their charge if they will rest for weeks. These are not rules to agitate over, but ideas that harmonize with the faint rhythm inside your devices. The gentle rhythm continues as your eyes soften and your breathing lengthens. As we come to the end of this quiet walk, return to the present room, to the soft pillow, to the small sounds around you that signal a safe, ordinary evening. The battery in your device is aging right now, in real time, the way we all are, at a pace that is too slow to notice and comforting once you understand it. Thank you for spending this soothing time here. If this gentle story helped your mind unclench, a like and a subscription help us keep releasing calm videos as often as we do. And you are warmly invited to drift through the playlist in the description whenever you need more soft company. Rest well, you are safe, and may your night be quiet and easy.